Welcome everyone and welcome Dr. Anita Walz. Dr. Walz is from Germany originally, where she studied biology until she had completed the equivalent of a master's at the University of Constance, right at the Swiss border. Dr. Walz developed an interest in ecology and environmental problems long before that time. During her last year in Constance, she applied for an exchange program with Oregon State University, where she initially studied oceanography for a year and then joined the Bioresources Engineering Department for an American master's degree. Her thesis was on dead plant matter accumulation in an artificial wetland that was constructed as one stage of pulp mill effluent treatment. From there, she moved on to the Marine Estuarine and Environmental Sciences program at the University of Maryland for a PhD. The program was interdisciplinary, and that is where she had her first exposure to geography. Dr. Walz learned GIS, excuse me, Geographic Information System and Remote Sensing Satellite Data Evaluation there, and had an excellent course in landscape ecology just when the field started to bloom. She then designed her dissertation research around all these techniques and examined the relationship between the occurrence of amphibian species, frogs, toads, and salamanders, excuse me, and their surrounding landscapes as derived from land cover data. She completed the degree in 2002. Dr. Walz came to Huntington when her husband got a job in biology at Marshall. She was an adjunct for 1 year teaching Math 121 and GIS for Dr. Mike Little, Integrated Science and Technology, IST. During this year, a position in geography was posted and Dr. Little recommended she apply for the position. The Department of Geography was looking for a natural scientist with a background in environmental studies, GIS, and remote sensing. Dr. Walz stated that this was a 100% fit for her. Although she did not have a geography degree, Dr. Walz has been in the geography department since that point in time, teaching physical geography, 3 different environmental geography courses, principles of GIS, and raster GIS. She has also taught the capstone course and just started teaching our comprehensive assessment course for grad students. So, wow, Dr. Walz, this is quite impressive. And thank you for being here. And I'm going to turn the meeting over to you now.
Well, thank you and welcome everybody. And I'm still not officially a geographer, so I keep, bringing my biologist perspective to the geography department, but I don't think that hurts. So I was asked to actually give a presentation about climate and the movement, the migration of species. This is not exactly my area of expertise, and I would have had to dig up a lot of information first. So I asked if I could reroute this a little bit. And I do teach physical geography, where I have about 6 weeks or so back to back on weather and climate. And I decided to do a little bit of an excerpt of this to start with and explain the mechanisms of climate, and then discuss some of the effects of it. And of course, people play a huge role when it comes to this. I didn't know exactly how I should title this slideshow, so I really kept it simple. Because, I'm going to switch over for the second half to talk about the climate in cities, actually, not climate change per se across the entire globe, but climate in cities. And I hope it's neither too technical nor too simplified for you. I'm teaching the course usually to liberal arts majors, so it's for non-majors. Therefore, it is a little bit simplified what I have here, but you will see a few terms that may not be familiar to all of you. Okay, so I titled it Climate and People because there's so much I would like to talk about, and we'll see how far we get here. All right, now, there are the climate doubters, and I'm pretty sure you've heard of them, and maybe we have some among us, who knows. And one of the big arguments is that the climate change that it changes naturally. And this is absolutely true. There are natural mechanisms that make the climate change regularly. There are some Earth internal causes, so things that happen here on the planet that affect the climate. One of them would be volcanic eruptions. We just had a supersized eruption again. There was one that happened, I believe, in the early 1800s, somewhere in the Philippines, that spewed an ash cloud into the sky that spread over the entire globe and caused winter during the whole summer season in Europe, for example, where their crops failed. But of course, volcanoes also contribute a lot of carbon dioxide, which has the opposite effect. We'll get to this. Carbon dioxide is a greenhouse gas and keeps us warmer. So anyway, continental arrangement, that's a little bit more difficult to explain. Just very briefly, you've probably all heard of the Gulf Stream that keeps the water nice warm along the East Coast. That Gulf Stream moves on up into the North Sea, towards the North Sea and the Arctic Ocean, and it delivers warm water up into the Arctic. Without that Gulf Stream, Europe would likely be frozen. So if the continents drift, at some point the Atlantic Ocean opened up and the Gulf Stream became possible. And really, we don't know what the climate was like before that in the part that is now Europe. There are changes in polarity of the Earth's magnetic field. Basically, the magnetic field protects us from a lot of space radiation. So if the magnetic field weakens, which it does on average every 200,000 years, a lot more dangerous radiation can reach us. Okay. Now, from the outside, there are causes as well. The sun's luminosity, so the sun's intensity, has actually increased since the Earth's beginning. So it does get warmer, but very slowly, obviously. There is a sunspot cycle. Every 22 years, the sun has a hotter part that is directly facing us, sending more intense radiation towards us. Then the Earth's position with respect to the sun changes a little bit as well. And this all cycles around. These astronomical relationships between the Earth and the sun, they were mathematically calculated by Milankovitch somewhere during World War I. I think the interesting thing about him was he's a Serbian, he was supposed to go into the war. I don't know if he defected or just never went in the first place, but they stuck him in prison. And they allowed him to have a pen and a pencil. Obviously, back when there were no computers yet, well, pens, pencils, paper, it seems unlimited quantities. And there he sat. He was a physicist, and he calculated what would happen backward from the time where he was living. So let me show you what he was looking at. I have this bar, hold on. So anyway, the Earth is really moving around the sun in an elliptic shape, so not a perfect circle. And sometimes this ellipsis is more flat, so it passes by the sun more closely during 2 seasons, and then it's further away during the other 2 seasons. And sometimes the circle is more, or the ellipsis is more circular, more spherical. This cycle changes every 100,000 years. So 50,000 years, it's a very elongated ellipsoid, and then the next after 50,000 years, it's closer to a circle. Then the Earth axis wobbles. We know that the Earth axis at this point right now points towards Polaris, the star, a really bright star in the sky. But this is not always the case. It kind of wobbles around over 26,000 years. So in 26,000 years, it will be pointing at Polaris again. In between, it will point away from it. Then there is a 40,000 year cycle where the axis tilts a little more or a little less. And the more the axis tilts, the more energy we get in polar regions. Because the sun comes in and actually reaches the northern hemisphere right here during our summers. If the axis was perpendicular to that path we describe around the sun, the polar regions or the North Pole itself would basically not get any energy. It would just skim right past it. So you can see there is a 100,000 year cycle, a 40,000 year cycle, and a 6,000 year cycle. They don't align with each other. So
Dr.
they all
Walz,
happen at the same time.
Dr. Walz, I'm sorry to interrupt. We are only seeing your first screen. Have you advanced your first screen?
Yes.
Okay, we are only seeing the very first one.
Oh, that is not good.
It is not advancing. I see on the side, we can see it on the side, but it's little, but on the
Okay,
big.
I'm clicking on new share. Let me try this.
Okay, I'm
But
sorry
you
to
may
interrupt.
see yourself then as well.
Oh, perfect. There we go.
You see the next slide?
Uh-huh.
Okay, so I
Something
think
about,
this is the first one that actually has the images on it. So
it's something
the
about
others-
something hypotheses. I can't pronounce the first name.
Milankovitch hypotheses. Yeah. Let me
Yes.
know. I will let you know when I advance next time. You tell me if it gets stuck again, please.
I will. Thank you. And thank you to Dr. Walker for bringing it to my attention. Thank you.
Okay.
I'm sorry.
Sorry
Okay.
about that.
It's okay.
Okay, so anyway, there are these three cycles that overlap, and Milankovitch, he sat in his prison cell happily with his paper and pencils and calculated back from the time where he lived. He knew the constellation at that point in time, and so he calculated thousands of years back. And I did actually flip this chart upside down on purpose, not because I was drinking too heavily. Okay? The reason is that most of the charts they show when it comes to climatic fluctuations, they start in the past on the left and they have the presence on the right. And this chart was drawn the other way around. I didn't want to have you to rethink when you look at the next chart at the bottom. So these are the calculations he made. 0 means the time where he was doing all the calculations. 50 is 50,000 years before that time. And so he came up with a fluctuation. You can tell the top is warmer. The top is colder and the bottom is warmer, also matching the chart at the bottom, which comes from other evidence. Okay, so you can see the climate does fluctuate naturally. At least this is the theoretical version of it. They laughed about him in the 50s, and in the 70s, they then came and did ocean cores and evaluated all this. So in the ocean cores, they found evidence of plants that live mostly during, or of algae that live mostly during the cold periods. And then sediments layered on top that came from a warmer period, and these layers, they alternated again and again. So there are, here's an example of a deep sea core. This actually goes much further back in the past. It goes 1.8 billion years back. Yeah, no, actually 1,870 years back in the past. Again, the top is cold, the bottom is warm. This is all relative. None of these axes is actually labeled with degrees. That's because we can't really determine it that closely. But we can clearly state that there is evidence that there were, for example, pollen found that live in extremely cold conditions during certain times. Do you see my cursor too? I'm hovering over one of the cold peaks, cold spells.
I saw it. Try it again.
Okay, I'm moving it a little bit.
Yes, yes, I see it. Yes.
Okay,
yes.
Okay, good, thank you. So this year was one of the cold spells, one where the glaciers expanded. We are now over here on the right-hand side, and we're dipping more into the warm spells right here. And so naturally we're in a warm phase, but there's a lot more to this. So these are the natural cycles. I am advancing to the next slide. Please let me know if you don't see it. Okay, good. So anyway, most of these natural phenomena, and of course the entire climate is powered by solar energy. And solar energy is really electromagnetic radiation, or rays as well. And there are many different wavelengths that can occur here. So the characteristic of the electromagnetic radiation is based on the wavelength of the rays. The shorter these wavelengths are, the higher is the energy level. So heat and light are actually both identical forms of energy. They are both electromagnetic radiation, but they differ in terms of their wavelengths. The scientific symbol for wavelength is lambda, the Greek letter for L, and here in this chart they show it with a capital L. So wavelength from crest to crest. And you know that light has a fixed speed. So no matter which of these wavelengths it is, it would cross this distance on my slide at the same time. You can probably imagine that the ray at the bottom would look much more nervous doing that than the long wavelengths on top. So we can draw out the electromagnetic spectrum, which is kind of done here with the short wavelengths. So the high energy wavelengths on the left, and the long wavelengths on the right. And you may recognize some of these terms like TV, radio waves, radar, microwaves. We have infrared in the middle, to the left of it, UV, and I'm pretty sure you all have heard about ultraviolet light being really dangerous. Don't spend too much time in the sun, right? But then X-rays are even worse. So you would definitely not want to spend as much time in X-rays. And then gamma rays are even shorter in terms of wavelengths. So I guess this kind of shows you that the shorter the wavelength, the higher the energy. The higher the energy, the more damage it can do. We don't like UV. We definitely don't like to sit exposed to X-rays, and gamma rays, that's radioactive. So we definitely want to stay away from those, okay? So here is a white bar that was cut out because this bar is important to us. This is what we receive from the sun and what the earth is also emitting. We are zoomed in at the bottom to this short stretch here. And again, to the left, shorter wavelengths, to the right, longer wavelengths. You see the near ultraviolet, and then through all the colors that we can detect with our eyes. And then the wavelengths get longer and longer through near infrared, which is something that healthy leaves emit, rocks with shortwave infrared, fires, middle infrared, and then thermal infrared is what the Earth's surface emits. And this is important because this is the kind of radiation that causes the greenhouse effect, or well, that the greenhouse effect is affected by. Silly way to say this. Anyway, so there are, as long as an object is warmer than absolute zero, and as far as I know, all objects are, they emit radiation. The hotter the object, the shorter those wavelengths are. So the sun is a really, really hot object. It has thousands of degrees, and it emits what I'm going to call shortwave radiation here. A lot of it is in the visible range, but then the UV, the gamma rays, these are all part of it as well. Luckily, gamma, UV, and the X-rays are filtered out in the upper atmosphere. They don't reach us, except for a little bit UV. The Earth is much cooler. We can touch it. None of us would want to touch the sun, right? So since it's much cooler, it's emitting longer wavelengths. So this is the thermal range now, thermal radiation, and I will either refer to it as long waves or as thermal radiation on the next few slides. And then there's the other thing, we're getting that energy in from the sun all the time, well, during the daytime anyway. The energy cannot be created or destroyed. It has got to either be converted into a different kind of energy, or it's got to be reflected and sent back out to space. So the reflection and the absorption and conversion, basically, whatever is absorbed does get converted. Those two have to add up to 100% of what is coming in. And I just wanted to say, show you just quickly, the reflection, the brighter the surface is, the more is actually reflected. And we get back to this in a short while when I tell you about a feedback mechanism. So clouds from above are really blinding. They are really bright. If you've ever been in an airplane, they reflect up to 80%, depending on how dense they are. Fresh snow, really clean still, 85 to 90%. Dry sand, the tan color is really bright, 35 to 40%. And here are tropical forests. If you ever look at a satellite image of tropical forests, they look really dark. And that means they don't send much visible light back towards us. They are absorbing a lot. Okay, so tropical forests, they only reflect 3% and 97% are absorbed on average. And on average, across the entire Earth, we reflect about 30%, which means 70% of the incoming radiation is being absorbed and converted into another kind of energy, because it doesn't just get destroyed or disappear. So let's talk about the absorbed components. And there are a few main options. So the trees, for example, they absorb the energy and then they conduct photosynthesis and they convert it into chemical energy. So into plant material, initially sugar, and then plant tissue, and just organic substances basically. And these organic substances, they are then storing the energy. Sometimes until we eat them, sometimes until they decompose, and sometimes they get covered up and turned into coal deposits, and then we use the energy when we dig it back up and burn it. Okay, so that's all old plant material where the sunlight was trapped and turned into chemical energy, and not destroyed, deposited in this case. The sunlight can also warm up the surface, which means it's now no longer visible shortwave energy, but now it turns into thermal energy. So it gets absorbed in form of shortwave radiation, and then it gets emitted again in form of long wave radiation, released this way. Okay, and then water. This is something that's a little harder to imagine, but when water evaporates, it actually stores energy as well. This is called latent heat. And latent heat is not heat as we imagine. It cannot be measured with a thermometer. It cannot be detected as a temperature change. It is just a name that the physicists came up with for a different form of energy. So latent heat, and as long as the water is in form of water vapor, it will hold that energy. Okay, it stores it. And this energy is why hurricanes, for example, fire up over warm ocean surfaces, because there a lot of evaporation is going on and latent heat can be picked up this way. And why hurricanes usually die off over land where the warm ocean surface is no longer available to charge up the system. Okay, so latent heat does get released when water condenses or when it freezes, and it condenses as it is rising in the atmosphere, forming all those clouds, those major rain clouds during hurricanes. This is where the energy is released, and that is what really drives the system. Okay, so let's look quickly. Sun rays come in, the blue waves are indicating shortwave radiation here. Again, they could make it through the atmosphere with no interaction. So we're focusing on the atmosphere, which is important when you want to talk about the greenhouse effect, right? So some of it makes it through straight to the ground. That doesn't do any damage yet. Case B, it scatters. There are some molecules that will send the energy right back or in all directions. And case C, there are certain types of molecules in the atmosphere that can actually absorb the radiation. And of course, the molecule, once it releases this energy again, it is now not 1,000 degrees hot or several thousand degrees hot like the sun. It is much cooler. So what it emits, because it's cooler, is a longer wavelength. So it emits long wave or thermal radiation. Okay, this is one part of how the atmosphere is heating up. And then there's the counter radiation. So we have these molecules that have the capacity to trap the radiation. Not all the atmospheric molecules do, but there are some of them. And as they trap the energy, they can't hold it forever. They will release it again, but the release is then in random directions. Some of it goes up and leaves us, and some of it gets sent right back down towards us. And this is called counter radiation. Right? So I kind of compare this, this is highly simplified, to a down blanket. You cover yourself in cold winter because you want to keep the heat trapped near you, right? The heat is trying to leave you, and then the down basically traps it and sends it back down to you. And this is basically the effect we have in the atmosphere with the molecules that can do that. They trap it and they send some of it back down towards us. And the more of these molecules that are in the atmosphere, the thicker our down blanket. Okay, the warmer it keeps us. So let's see, this is all long wave radiation. So thermal radiation that does keep us warm. So let's talk quickly about the various molecules in the atmosphere. We have 78% nitrogen. This is really an inert gas. It doesn't react with anything. It doesn't do any damage. And it does actually require highly specialized organisms to turn this into something useful for everybody else. So microorganisms, for example, that live in the soil, on plant roots, like the legumes, like peas and beans, and so they are able to trap N2 as it is and turn it under huge energy input, turn it into a different form that is then useful for plants and can be turned into other substances that we need in the end as well. Nitrogen is a lot in proteins, for example. Oxygen is a reactive gas. Without oxygen, we wouldn't be able to burn anything. It's produced by green plants during photosynthesis. They pick up carbon dioxide and take the carbon out, turn it into organic substances. And their waste product is the oxygen, O2. So this goes back in the atmosphere, 21%. If we had more oxygen, we would have more fires as well, because it is such a reactive gas. And then there's a noble gas, argon, 1%, that almost fills it here. It's completely inert, it cannot react with anything. And then we have variable gases. And if you look at this list, they are going to show up again. Those are the ones that have the greenhouse gas effect. We know about carbon dioxide, CO2, and I did put in a concentration there, but this has changed a long time ago. When I was a child in school, the average was listed as 0.028, if I remember that correctly. I think we're near 0.04 now. It's variable because A, it's going up with the changes that we cause, but B, it also fluctuates summer and winter. In the summer, when the trees are green in the northern hemisphere, they pick the carbon dioxide out of the atmosphere, turn it into oxygen, and use the carbon for organic material. In the winter, the leaves drop, decompose, and the carbon is released again in form of carbon dioxide. So in the winter, carbon dioxide concentrations go up, and in the summer they go down. It's a regular cycle, but very slowly the concentration over the many years go up, up, up at this point. So the water vapor, water is a greenhouse gas. This is important as well. Depending on the temperature, I'll show you on the next slide, between 0.1 and 4% of the atmosphere. Methane is produced by cows, termites, released in swamps. It's also released when we dig for coal, I think mostly when we drill for gas, for petroleum. And they flare it, which, I mean, theoretically, we could just trap it and then heat houses with it because it's natural gas. But I think it's cheaper to flare it, but at least it would turn into carbon dioxide, which is already better than methane itself. Methane is a tremendously potent greenhouse gas. I think it's, as far as I heard, somewhere between 20 and 80 times as potent as carbon dioxide. Okay, so it can do much more damage, but it doesn't stay in the atmosphere quite as long. It reacts and gets turned into carbon dioxide. And of course, you can't flare it if it comes out of a cow or termites or swamps, because those are not point sources. They are scattered all over, and you cannot just turn it into carbon dioxide by burning it or trapping it. And Chlorofluorocarbons are totally man-made substances. We're not going to look much into these today. And then dust and particulates, pollen, sea salt, volcanic dust, and soil, these are also variable and they can also affect the climate. So the greenhouse effect now. They're radiatively active trace gases is another word for these. And again, here is our carbon dioxide that I just mentioned. This is ozone, water, methane, chlorofluorocarbons, and nitrous oxides are among them. Okay, those are just the most important ones. They absorb the long wave radiation, the thermal radiation, and then they re-radiate it in random directions. And the more of these gases there are, the more chance we have that this radiation gets sent back down to us. So we get the counter radiation. Okay, so the warmer we would get because we trap the radiation. There is, of course, atmospheric mixing. There are no walls in the atmosphere, which means wherever there is a source, the material, these substances would get picked up and then distributed worldwide. Now, greenhouse gases are actually necessary. Without the greenhouse gases, the Earth would be 30 degrees colder than it is, and we would be on a pretty much frozen over planet. There might be small regions that would be thawed. So it's good that we have this effect, that it protects us a little bit. So that's a good thing, but the problem is how much of a good thing is still good, okay? Can there be too much of this? So as we add more of these greenhouse gases in the atmosphere, it's basically as if we're turning up the thermostat. So I mentioned that water's a greenhouse gas too, and we have to keep in mind that the warmer the air, the more water it can actually hold. And you probably almost feel the greenhouse effect if you live in Huntington and have to live through those muddy summers, right? This has to do with the heat index as well. So when it is really muggy, it feels much hotter because of all the water in the atmosphere. And so warm maritime air, which is what we mostly get in the summer, it gets blown up from the Gulf of Mexico with a lot of humidity, comes invades our areas. It can bring a lot of moisture along with it, while at the poles it is so cold that there's very little water, which is why it snows very little at the poles. What we expect, what could happen is that it actually snows more at the poles as the climate warms up because the air can suddenly bring more moisture in. Right. So here are a few measurements of greenhouse gases. On the right are charts that are from the Intergovernmental Panel on Climate Change. So these are scientists from all over the world that get together fairly regularly, and every few years they come out with a report. I believe this is from the report from 2007. Just to show you, we have carbon dioxide on the top and methane next. There are nitrous oxides, all three of them are greenhouse gases. The concentrations, they went up and down a little bit, and then suddenly things went crazy. And what we have here is a little insert on each of these charts that starts at the beginning of the Industrial Revolution in 1750, and then up to, well, today basically. And you see that initially it started rising a little bit and then more and more and more. Now, what happened during the Industrial Revolution? First, we had to develop the industry. Second, there were only a few countries that could actually afford all these luxuries. So the development of the countries, it started picking up later on as well. And the third is that the population of the world grew tremendously since. So this is why this curve gets steeper and steeper, because there are more people demanding goods, there is more industrial activity, more countries are developing, and this is why we are now producing more and more carbon dioxide, because we're still driving most of the industry based on coal and petroleum. So substances that are being burned and turned into carbon dioxide and then spewed into the atmosphere, basically. So these are the findings from the International Panel on Climate Change, IPCC. And down here, we actually have a climate record starting in 1700. So you see there are natural fluctuations up and down. It was cold in the early 1800s, and then it started climbing. And after World War II, the industry definitely picked up, and more countries started developing and all. And ever since, we have been beating one record after the other. This chart cuts off in 2000. And I can tell you, I don't have the data to show you right now, but it just got worse. It keeps climbing upward. Okay, let's see. So yes, the climate does cycle naturally, but humans have an impact as well. Here are charts. These are theoretical charts where the IPCC ran models. The blue part, they took all the natural effects that they know of, the physical effects, and they calculated what the climate would do, and they came up with this blue range here. So the years passed on the left, today on the right, the temperature gets higher as you go up. The pink model is where they added in the effect of the extra carbon dioxide and methane into their models. So the pink was predicted, including the anthropogenic output, including the output that we have added to the atmosphere. And here, the black is actually what was observed. And you can see it follows the prediction that includes our effect on the climate as well. Okay, and so what we are doing is we are following natural fluctuations until we put out too much, and then we're basically just putting heat on top. We're turning up the thermostat artificially. Underneath, it will still fluctuate naturally, but we have added. So whatever fluctuates naturally just happens at a higher temperature now. Okay. And yes. There are also a few feedbacks which seem quite natural. So, and the regions, the polar regions, are actually much more strongly affected by global warming. If you ever watch the news, of course, they don't pay much attention to to polar regions because we don't really do much up there. But if you, I guess once you've heard this, you may start picking this up in the news. There are positive feedback mechanisms, which sounds like a good thing, but positive basically means if something gets triggered, the reaction of the system is such that that trigger gets even worse. It enhances it in a positive way, which is really a negative thing, a bad thing. Those turn into vicious cycles. So, for example, I told you that ice and snow is really bright and it reflects a lot, right? Which means there is little left to be absorbed. The problem is, as it gets warmer, the snow melts and the ice melts, and then more of the dark surfaces are exposed underneath it. They reflect less, they now absorb more and turn it into thermal radiation, which means that environment is now warming up right there. Lower albedo means lower reflection, higher absorption, and if it warms up, if the dirt that is suddenly exposed right there warms up, it will melt the snow next to it and the ice faster. Did you ever notice when snow falls here, the moment some dark surface sticks out, like the pavement or so, around it, it starts melting faster than the snow that is still intact. That's basically the same effect right here. So as the snow melts, it gets warmer. As it gets warmer, the ice melts, more gets absorbed, and the system warms up even more, and more ice melts faster. So it's a runaway effect. And this, of course, happens wherever we have ice surfaces. High in the mountains, we have heard about glaciers disappearing. and also in the polar regions. This is a big issue down at in the Antarctic, and then the Greenland ice sheet is melting rapidly as well. Here's another one, also affecting polar regions. The tundra has permafrost, permanently frozen ground. And the ground, so this is not just water, it's all the soil mixed in, and there's a very high content of organic material. So like frozen peat, moss, this kind of thing. And as it gets warmer, no matter what triggered it, this could have been us adding carbon dioxide to the atmosphere. The tundra starts thawing. And as the tundra thaws, organisms, microorganisms can now suddenly live in there and decompose the material, the dead organic matter that is in there. And as that dead organic matter, like peat, moss, and all that gets decomposed, it releases carbon dioxide and methane. So more greenhouse gases that initially warm up the area where it got released, and then the circle gets even worse again, you see? More greenhouse gases warming up, it thaws even faster, but at the same time, this also gets blown around all over the globe because carbon dioxide and methane are now in the atmosphere. And what is happening in the tundra, I think up to about 1980, the tundra was a sink. So this cycle was going in the other direction. It got colder. And organic material that grew over the summer simply froze and wasn't available to decomposition. And therefore, the next year, more material was deposited on top of it. In around 1980, this cycle switched. And it turned from a carbon sink into a carbon source. And ever since, more carbon dioxide and methane have been released up there, from up there. And that, of course, spreads worldwide. Now, that sounds like a natural cycle, but the initial warm-up could very well have been triggered by us, the warm-up beyond that turning point anyway. Okay. Now, there are a lot of consequences of the warming. For example, remember I told you that the storms, that the warm air can hold more water vapor. Water vapor has energy that gets released, and that kind of, in warmer climates, we get stronger tropical storms. Circulation patterns change. So we do have pressure belts all around the Earth. And as one region gets warmer, this region expands and pushes other pressure systems a little further away. I guess you could picture this a little bit like holding on to a whole bunch of balloons. And if you were able to just blow up the balloon in the middle a little further, it pushes the others outward. And along with it, the others shift, they get pushed around. So it's pressure systems that shift across the globe, where in some regions this may mean that we suddenly have less rainfall. In other regions, we may suddenly have more. So when we talk about global warming, we should really switch terminology and use climate change instead, because it could get drier in some regions, wetter in others. It gets warmer in most, but there are actually a few where it could also get a little bit colder. Then, with all this, I already mentioned the ice caps in the Arctic, on Greenland, and in the Antarctic. There's a huge amount of ice that is actually sitting on top of the continent. And if this ice melts and flows into the ocean, it will cause sea level rise, or it is already causing sea level rise. And then the oceans will flood inland, especially in fairly flat areas. If you think about it, Bangladesh, a very poor country already, 28% of it is within 2 meters above sea level. And there's enough ice. If we, worst case scenario, if we melted it all, the sea level could rise about plus 80 meters. So it could come up by 80 meters. If we just melt half of this, 40 meters, already very disastrous, okay? These changes, they could be so fast that ecosystems and organisms have a hard time adjusting and moving. And moving is not always possible anyway. If we think about the red spruce here in West Virginia, it used to be scattered across the Appalachian Mountains, and it likes it cool. It got warmer here, and so the red spruce is now found on the very top of the mountains. The higher up you go, the cooler the climate gets. But from there, it can't just move forward. It's stuck on top of the mountain. It's a little bit like an island, you know. We would have to cross, I don't know how many valleys to reach the Arctic this way. It is known that with previous climate changes, species, even tree species, have moved. The Arctic has mostly the coniferous trees, needle trees, and they used to be much further down in the Appalachians, for example, further down south, I mean, during colder climates. If the climate adjusts slowly, they can retreat slowly. If it happens too fast, they may have trouble because after all, trees don't have roots they can walk on, okay? They are kind of stuck. They depend on other ways to spread their seeds. So let's see. There's another big thing that people don't think about very often. There are infectious diseases like malaria that is transmitted by mosquitoes. Malaria was not, if you reach a climate that is cold enough over the winter, malaria cannot survive there. And they have experienced, we are experiencing a forward migration of malaria now, and there are many other diseases that can do exactly the same thing. Okay, so something, if it just doesn't get killed off over the winter anymore because there is no more deep freeze, that will become an issue. I put this map together for you just to show what sea level rise could do, to go back to that quickly. Remember, I don't have a world map here. This is just the eastern United States. I told you Bangladesh has 2 meters, a third of the country within 2 meters. Here, I used this light blue color to show you what would happen in the US if the sea level was to rise by 2 meters. Do you see what happens to the tip of Florida? To New Orleans here in Louisiana? How far the water would go in if it was only 2 meters? Okay, we would see some effects in the in the Carolinas, all the way up basically the Atlantic coast. I also simulated 10 meters. That is the next shade of bluish green right here. Okay, and if we were to lose all 80 meters, if all the ice was removed from Arctic regions, we would actually lose Florida. It would be gone, and most of Louisiana would be gone as well. Okay, so the coastline of the United States and the worst case scenario would look like what is left in gray on this map. Okay, so as the sea level rises, I think they expect maybe 1 meter rise in 100 years. So it's not going to affect us all that much anymore. But with every storm, those big waves can come in further into the continent. It is an issue that we have got to be careful with. I personally think that if an area gets flooded that is very near the coastline, they should resettle instead of rebuild. I do not find it a very smart approach to just rebuild at this point. So there are other consequences. If you think about it, it's not just the Arctic that has big ice sheets. We used to have mountains with huge glaciers. The mountains are still there, but the glaciers are disappearing. And with all the snowfall we have in the mountains, there are a lot of societies that live along streams below mountains, and these streams used to bring year-long meltwater. I believe Mount Kilimanjaro in Africa is one of these cases. There are people, villages underneath it that lived off the meltwater throughout the entire summer. Those glaciers now have almost disappeared, which means the rain runs down those creeks whenever it does rain. And during dry periods, those creeks are running dry. So these societies now have to suddenly figure out how to live without their water supply. And that is definitely an issue. Most people have moved to cities now. And I don't know if you noticed on the map that I just showed you. Let me go one page up again. A lot of our major cities are actually very, very near the ocean. And this is the case worldwide because I guess there was just a lot of really good fishing and all. There are a large chunk of the population is within coastlines. So whenever the sea level goes up, this could cause a big disaster as well. And then there are island nations like the Maldives. Well, I mean, Bangladesh is not an island nation, that should go in front. But there are nations that are really near the sea level, and I expect that there are going to be mass migrations of people. I heard a news report, the Maldivian president years back, where they said they're actually trying to buy up land elsewhere so they can resettle because their islands will simply go. The entire islands are within 2 meters of the sea level. There is no spot that sticks up above it. So let's see, just very quickly, I told you that the output of carbon dioxide gets worse because of increased industrialism, because of increased development across the earth. But at the same time, the population is growing. And as there are more people, we need more food. If they're all as spoiled as we are, we're going to demand a whole bunch of resources for ourselves, right? And our consumption just gets worse. This is a population density map of 1950. And as I push, I will add 20 years each. Green means low population density. Red means really dense. So you can tell Europe is very densely populated. The central part anyway. India, China's almost there. They will get there in no time. Japan over here is very dense right already. The US, not so much. There are a lot of open areas in the United States. But go and focus on Africa, for example. This is where the birth rates are greatest. Okay, 1950, 1970, the US has just turned orange as well. 2000, Nigeria is growing really fast. So that's this red, dark red blob right here. Okay. 2020, even the central part of Africa where there is hardly anything to live off has turned yellow now. Okay. And this is the prediction into 1950. Did you see Africa turn from a green country into something that is almost all orange and red? Right? And we have to feed all these people. I mean, all us people, I have to say, we've got to come up with a way to feed everybody. Okay? And I don't mean the Africans, I mean everybody. So fixing the climate, well, I put a great big question mark back there. How is this even possible with what we've done so far? It would require many different approaches. And I guess initially the best goal would be to try to stop emissions, to not make it any worse than it already is. And the climate would still worsen because there's this lag phase, remember, such vicious cycles as we have in the Arctic. Okay, and then really fixing it would mean we would have to remove carbon. And they are talking about carbon sequestration today, where they have factories that could plug carbon out of the atmosphere. I don't know how much energy this would take to even start. Okay. And then again, we are working against a growing population that needs more food and more living space all the time. So there is the development, the cities, the roads and everything. Then there's agriculture trying to feed us all. And then there are the natural spaces and they all compete with each other. What do we choose? Do we grow the food we need for a growing population? Or are we going to try to plant trees? A lot of times they say, well, let's do this. This helps fixing the climate. Okay. And of course, that's just one step. There are many other things that should be done and could be done, but the tree plantings, they have been, I would think that a lot of industrialized nations are using this as an excuse. they are claiming they are planting trees in, to try to get carbon neutral. Problem is, if you look at places like Germany, they're so densely populated, they don't really have space for new forests. So what they try to do is plant trees elsewhere, like in the Amazon. And then they suddenly try to tell the Brazilians, well, you have to leave your forests standing. So I actually saw something in Germany that I wanted to talk about very briefly. I believe what they did over there is they came up with a law to try to fix the climate, where they say, well, if you own land and you plant trees, we will give you so and so much money for it, for every tree. So when I walked through the forests, I go there, I try to go there every summer. Last year, I noticed tree plantings, oaks that grow huge usually, right? They were planted about 2 feet apart in rows, and the rows themselves were only spaced about maybe 3 feet, 4 feet or so, so that a tractor, a very narrow tractor that could still drive through, like the ones that go through the vineyards. And I was wondering what the point of this is, because out of these many trees that are standing so close to each other, only maybe 10% maximum could survive, if at all. And they are not like the tree plantings that are going to be dug up and spread elsewhere. You know, it's not just the startup, what we call tree schools in Germany. I don't even know if you use the same term in the US. It's not that they plant. Sorry. It's not as if they plant those trees to transplant them later. I do believe that they are getting money per tree, and then there is no follow-up. Nobody checks in on whether those trees survive or not. So I think that these are landowners that are abusing the free handouts. Okay, so it's backfiring. This is not going to solve the tree problem, the climate problem, if we do this. And the problem is there are no feedback loops. Nobody's going in to check if this is actually done properly, if the trees are planted in a way that they can grow healthily. And they cannot the way they are planted right now. Okay. So anyway, let's look at other trees. I am very curious about trees. I came to Huntington. I was amazed about all those roadside trees we have. I find them really pretty. And where I come from, we don't leave as much space for urban trees themselves. So I wanted to see what they do. And so I looked at the urban heat island, which is a well-known effect, basically. And I looked specifically at those trees that are planted along the roadside. Okay, let me explain the urban heat island first. The cities, this chart at the bottom shows it real nicely, and this is widespread, shows up in every textbook basically. Cities are warmer than their surrounding rural areas, and there are multiple reasons for it. One of them are heat sources, such as cars, their exhausts, the engines, the HVAC system, heat and air conditioning. Of course, they run as well and run hot. Have you ever felt the back of your fridge, for example? And the industry, people, yeah, of course, people heating their houses and maybe not necessarily being insulated too well. Then the urban structures, they may change some wind patterns. It is possible that they block the wind in some places, and therefore the heat accumulates there like pockets. And then in red, I showed the part that I am very curious about. There are sealed dry surfaces, so like rooftops, parking lots, and any kind of road pavement. These dry up, we route the water away really fast because after all, we don't want to get flooded, right? So we have drainage systems on the roads. So the roads dry really fast. And once they are dry, they can't do anything but absorb the solar radiation and then heat up really bad. And then typically they release the heat very, very slowly overnight. So let me look at the chart quickly at the bottom. The red line shows you the temperature. The lower the curve, the cooler the temperature, the higher the red curve goes, the warmer the temperature. Over vegetated areas, it stays cool because the solar radiation, remember, that comes in gets absorbed by the trees and turned into chemical energy, or water gets evaporated. And the more we seal the ground, the more structures we put up, the warmer the temperature gets. Typically, downtown areas are the hottest because in downtown areas, there's least space for greenery. Okay, so city parks can depress the temperature in the middle, but this effect only lasts to about 1 block away, 1 housing block away. And then you run out of that cooling effect. Now, I am looking at trees that are planted along the roads. Trees have the benefits that they absorb the solar energy and don't allow it to turn into sensible heat, into a thermal radiation. So they pick up the energy, use photosynthesis to trap it as chemical energy, organic material in their leaf matter and all. Then they conduct transpiration. They have to evaporate water from their pores so that new water can be pulled up from the root, bringing new nutrients upward. And evaporation basically leads to latent heat, which does not result in a temperature change. All this prevents the warm up. They also sequester carbon dioxide, which means they pick carbon dioxide out of the atmosphere. They keep the carbon, turn that into the chemical energy, and they release oxygen, O2, which is not a greenhouse gas. So another little effect that reduces the greenhouse gas effect a little bit. Remember, during the summers when the trees are green, carbon dioxide concentrations go down. In the winter, they go up. Okay? But then there's the extra effect. And that's if you plant those trees along the street, for example, and if you plant wide trees, then they intercept the radiation before it ever reaches the pavement. If the rays don't go down to the pavement cannot heat up, and it is not going to turn into that nighttime oven. Okay. And if you have narrow trees, this here is symbolizing my Bradford pear. The pear trees, they try to grow straight up and really narrow. They don't shade a wide area. Okay, then there may not be any benefit to shading the road. How many of you actually like parking under trees in the shade in the summer? I always choose the shadiest spot, right? Bradford pears don't really help much when it comes to that. So anyway, here are just a few images. These are really nice big oaks that reach out into the street, and you can tell the cars are clustered in the shade, and they really shade well, in this case, it's not pavement, it's cobblestone, but they shade it nicely. So Huntington has a lot of trees, even along the roadside. It's a Rust Belt city with a limited budget, and that's a little bit problematic. The residential areas, they are still characterized, or many of them, by mature, large growing trees. But because the budget is limited, the city went there for a while and started removing trees. It costs almost the same whether you remove a tree or you trim it back. The problem with it, if you trim the tree back, is that 5 years later, you've got to invest the same money again and do it again. So it's a whole bunch cheaper in the long run to cut the trees down, remove them, than it is to maintain them. And these trees are in the city's right of way, basically, if they are between the sidewalk and the street. And the city came up with rules that are more or less followed. I would say less followed, luckily. Okay? They don't want any large growing trees planted in this green strip. I call it green strip between sidewalk and road. They don't want large growing trees. And initially the thought was because of power lines and utilities and all, although in this particular neighborhood, the power lines are actually in the alleys away from the road itself. But it's just one rule fits all is what they tried, I guess. So if, let me show you. The maple, this here is a maple that sticks almost entirely across 11th Avenue. Do you know how wide 11th is? From what I heard, there used to be a trolley going down the middle of it and back. And this seems to be the reason why they built it so wide. Oaks stick out really far and shade a lot. They were basically on the do not plant list, whether people stuck to these rules or even know about them or not. And then there are trees like the Bradford pears, cherry, crab apple. There's small growing trees that don't really benefit the road here in terms of shade, but they also have a short lifespan. Oaks grow much older than pear trees do, for example. Okay. So I did a localized field study. If you look at this, this is a satellite image that I received here. This wide street here is 8th Street. It goes to the park down here. There's Redder Park somewhere here. This is 12th Avenue and 11th Avenue. I picked 12 blocks along these two avenues. The green dots are the trees. I mapped these, and the red dots are where I actually took temperature measurements, and I tried to pick some that are out in the open on the pavement and some that are very well shaded, just so I could figure out how much of an effect these trees have. Here's another picture of the canopy. This here is 8th Street. 8th Street, the cars park on both sides, and then there are 4 lanes. And this oak tree that has since been removed actually stretched across all the way to the cars parked on the other side. This is how far an oak tree can shade. Okay. So anyway, I do GIS, Geographic Information System. It's a software that allows me to map and simulate and model and all this. So I was able to simulate my trees, to map them, including their canopy. And then I simulated what would happen to the shadow during parts as the sun moved across the sky. So here we have a morning example where the shadow is showing, pointing towards the west because the sun comes up in the east. Right? So I added this up throughout the day, and some locations get more shade. The darker it is, the more shade, and some less because there are fewer trees around. This here is 11th Avenue. This is this one intersection that is rounded. I don't know if you're familiar with this. This seems to have been the turnaround for that trolley back when. Okay. I don't know if you ever came through this neighborhood. If you ever do, pay attention to this. So I did map my trees. I checked where the shadow was densest throughout the day. And then I picked locations, the little red stars, to actually go out and measure the temperatures. Some purposely in the sun and some, of course, purposely in the shade. And this is what I found. So I had a thermal infrared sensor that you point at the surface and you click and then you write down the measurement. And I went out there during clear, calm summer days during a heat wave. I went in the afternoon. I actually had to do this spread over several days. It was too hot for me. I was starting to get funny heart flappings there because of the heat. And then after sunset, where I could pull it through in one shot. And then the next morning before the sun came back up, and I measured the temperature of the pavement itself. Okay, so in the chart on the left, we see the percent shade from an earlier analysis, 100% shade surrounded by trees on the right, 0% on the left. They all had a little bit of shade because late in the evening, the shadow even came across wide open areas. Okay, then I have a temperature on the y-axis, lower temperatures at the bottom, higher at the top, 60 degrees. This is on the Celsius scale. Let me see, 20 degrees is comfortable room temperature, I say. 50 degrees is where it gets dangerous for us. Our proteins are running into trouble and stop working. Okay, so this is where it gets uncomfortable. Now, this is again surface temperature, not air temperature. This is where you see the street and you do not want to take your shoes off and run across it barefoot. That's what I mean. This is why the temperatures get so hot. And the red points are the midday measurements, and you very clearly see the points are higher on the left and less shade than they are on the right in 100% shade. In the evening, there was a fairly rapid cool down, but there was still a very significant decline towards the shaded areas. It was still significantly warmer over in exposed areas. The green, I actually zoomed into the green in the chart on the right. That is the early morning before the sun came back up. I went right back to those spots that were hot during the day and measured where it's exposed a lot, little shade, and then a lot of shade. It's not quite as clear anymore, but if I run the regression analysis, it was still significant. So even in the morning, before the sun came back up to do more damage to our heat, there was still a 2-degree difference between the areas that were almost entirely exposed and those that were almost entirely shaded on average. Okay, so basically our roads are acting like ovens. They are charged up, burning during the day, and then they radiate all night, and the nights in the summer are not long enough to discharge all the energy. They keep going. Okay, now I just went there and measured. I picked spots, mapped every single tree, and that was getting quite complicated because it's localized. So a lot of labor required, detailed measurements, but I could measure individual trees. That was good. If you look at an entire city, you can't really go and measure it all manually. That doesn't work. So since I also learned remote sensing, the evaluation of satellite images, I came up with a way to get myself such images and then evaluate the entire city. It depending on your data source, this could get expensive. And there's a limited resolution. Let me explain that quickly. So the resolution, I will refer to pixels. Whenever you look at a screen, it is at an image, it's made up of pixels that are red, green, and blue typically. And if you were to zoom in to these pixels, you would suddenly see they are squares, one square next to the other. And zooming out, you don't see the boundaries that clearly anymore, but then you would get the whole picture. So here is I took this here out of a satellite image that has a very coarse resolution. It has 60 megapixels. This comes from satellite images that are free to us, so that's a good thing. And on top, I have a high resolution image. I'm going to show you the actual image in a moment, but these here are 4 megapixels. So much, much smaller pixels, 4 meters, maybe 12 feet or so. You see more detail. It shows you the same area, those two. Okay, so you get more detail out of higher resolution pixels, but these here cost an arm and a leg, while the coarser ones are free. That's basically what I'm trying to tell you. The other thing is, I needed, in order to map vegetation, I used what's called the normalized difference vegetation index. I'm going to try to call it just vegetation index, where you need a red channel and the near infrared channel. A regular photograph that you take with your cameras does not have the near infrared, so that's already a luxury, okay? And the near infrared, the satellites, they do give you near infrared. Then if you want to estimate the temperature, you also need a thermal channel. And the best I could find was again the free images from the satellites, thematic mapper, Landsat satellites, 30 megapixels, so that course right here. I was unable to find high resolution thermal images. So I wanted to see if I can even figure out whether this shows me the heat island properly, if the images are that coarse anyway. So what I wanted to show you here or tell you here is there's a way to calculate a vegetation index. And then there are ways to estimate surface temperature through various channels that you can get from satellites. Okay. Now, I think I already spoke about most of this. So where are the hotspots in the city is one of the questions. And the other question I had was, if I have 30-meter resolution for the thermal images, will it show me if individual trees, will it show me the effect of individual trees being removed and the next year the area suddenly being hotter because it's exposed now? So here is the result of my analysis. On the left, I have a high resolution image that cost me a lot of money, but I had some support through a grant. And from the high resolution image, I got my near infrared and the red channel. And so I was calculating the vegetation cover, vegetation index. Green means very well vegetated. Red means hardly any vegetation at all. The resolution of this is 4 meters. So one of the little squares on that image is about 12 by 12 feet. Okay, a square 12 by 12 feet. And you can clearly see greenery around the courthouse, downtown Huntington, while everything else is almost entirely paved over, hardly a tree in between. Marshall creates a nice green spot because we have really nice trees on campus here. There used to be a track field near Campbell Huntington or near Hal Greer. That one's been built over since, so this one would no longer be green. That used to be the turf right there. Riddle Park, of course, nice green. Then you can see places like schools. Here, this is what used to be Kamak. It's now Huntington Middle and Huntington, what is it? What do they call the elementary school? It used to be Kamak Middle and Elementary right here with a football field next to it. So half very paved over, very sealed, and half of it very vegetated. You see that? Okay. And then here's Riddle Park, very green. Oh, can you give me a short break, please? I think my dog may be having an issue. Do you hear him?
No, but if you need to, Dr. Walz, if you need to go, that's okay. We can. Well,
I just need to check in on him quickly. Sure. Could we just maybe take a 10-minute break or so? I'll pick it up. I'm almost done.
We normally wrap up around noon, so, but we can schedule a question and answer session if you need to go.
Let me just check what the reason for it is.
Okay, sure.
Elizabeth, can you hear me?
Yes, I can.
I'm wondering if at some point we could get into how climate change is going to change agriculture. She was talking about having to feed more and more people, but if the places where we can grow things are no longer going to be no longer being able to grow those things, it's going to affect where we grow things.
Right.
As the temperatures heat up, Florida oranges may not be as good. You know, they may be growing oranges in South Carolina and North Carolina.
I'm sorry, I'm back.
That's okay. That's okay.
It was not a seizure. It was him. He has issues with grip on the floor and panics. He's really old.
Oh.
He lost some of his mobility there, so he was stuck and had to pick him up and put him somewhere where he can walk again.
Sure.
I'm outside for now. Anyway, so there isn't all that much left in terms of slides, and then we can go and have question and answers. Okay, what I wanted to show you on this map here is how these, see here, this is an area that used to be Miller Elementary. This one's now green. See this? It's right here. The school was still up and standing. How this translates on the thermal map, you see that the resolution here is coarser, right? You can see the individual pixels. Those are 30-meter pixels now. Marshall, blue means cold, red means hot, and then of course yellows and greens in between. Marshall creates a cool island. And this area here, which still, it has large houses and a lot of greenery around them. All, I just don't have a name for it, so I didn't label it on my map. Also, a cooler spot right there. The track field makes a little bend in here towards Halgreer and out then, but Ritter Park is definitely very cool. Here is a slight hotspot where Kamak stands, this roof. And the city hall actually creates a cool spot in the city. Do you see this? But what you can tell is wherever it's sealed over in here, it's really hot over there. So we do have the urban heat island. This is it. We very clearly have it. You don't have to go to Chicago to see that. And over here, these are surface temperatures again, not air temperatures. And you can see the difference between them. The Ohio River, which doesn't have any vegetation, which is why it's red. That's the one exception here. It's red, but it's not hot. You see how cool it is, right? So I actually, and this is why I tried to explain the pixels here. Every pixel gives me a temperature value. So if I try to extract all these numbers for every single one of those pixels, I can then plot them. My vegetation index on the x-axis, the further to the right you go, the more vegetation I have. And the temperature on the y-axis, the higher up you go, the warmer it gets. And you can see how these pixels line up, right? How there's a very clear relationship between low vegetation and high temperatures. And as the vegetation increases towards the right, the temperature drops. With the exception of this blob down here, and that's the Ohio River. Low vegetation, but very cool, okay? So very strong correlation right there. What I did too is I tried to map the roadside trees now from satellite images because it's too much work to go through and do this all manually. So I can't do this all over the city. So I tested this again on satellite images in the neighborhood that I was in. And I got some high resolution satellite data. I found some free data that were taken. Typically satellite images are taken during the leaf off season because it's an agency that wants them to map roads. And when the leaves are on and the trees are hiding the roads, then the satellite images are often useless for these agencies. So it's easier to find leaf off or winter images. I got a March image for which I could then calculate the vegetation index. That's this one here. And you see they're still green, but you probably know that most lawns are still green in March anyway, right? What we see here are the lawns, the front lawns and the back lawns, and the house, the roofs, and we very clearly see the roads on this, all the red areas. Then I got a slightly coarser May image. I had to pay for that one. And here you can see that in May, the leaves were out. Here I could suddenly get a really good idea of how much of this road was shaded, was covered by canopy. Okay, and so if I compare the two images or take the difference between the two, that's at the bottom, I see the contribution of the trees themselves. How, then I can evaluate how much of the sealed surface is actually protected by the tree, by the shade of the trees. Okay, so it's kind of like a difference analysis, leaf off versus leaf on. I can distinguish between what is caused by trees and what is just lawn. Lawns don't shade the roads. Okay. Same difference, you can also apply differences before and after, basically. So you can take an image for 2005 and one for 2010. These are the two that I was able to buy. And then calculate the vegetation index for both and subtract. And then If you subtract the right way around, you will see where vegetation got lost. Here I displayed it in colors where beige indicates no change, green, gain in vegetation, and red, loss in vegetation. And this block here, that's Kamak. They tore down, well, they didn't tear it down. They reworked the building, so little change, still roof on half of the block, but they took out the football field on the other half of the block. And that is why this block is red now, it's vegetation loss. They built over it buildings, and I think they have a lot of artificial turf in there now. Not real vegetation, but artificial turf. Okay? And then you see other red blotches where they basically took down some major trees. Otherwise, you just see small changes. Okay, so that's a way to look at it. I could do this for the entire city, basically, and figure out where things got lost. So the good thing about those trees is they don't need much space down on the ground. We have a problem with the roots, yes, they have to be managed, and this green strip is probably too narrow for a tree that size. As I said, this tree's gone now. It stretched all the way across 8th Street, 6 lanes, 2 parking lanes plus 4 driving lanes. They have a very small footprint otherwise on the ground, so we could still use the ground, but they have a lot of benefit up in the air by shading our roads. If we were able to plant them strategically, we could do a whole bunch good for our urban climate. Okay? So measuring individual trees costs a lot of time. Satellite images would allow me to actually look at the city and figure out where areas are where planting may actually be useful, where there are bare areas. You can use them to detect change as well and look into people's backyards, at least at a very coarse resolution, just to check if there's vegetation there or not. Okay. So anyway, just for the case you're curious, I have the formulas here, and but I'm not going to talk about these right now. I doubt you're all that eager to copy my study. Right? Let's go back to the prettier picture. I think I'm pretty much done. Otherwise,
Okay, well,
it's noon anyway. Did I speak that long?
that's fine, because you had so much to share with us. And so do we have questions very quickly for Dr. Walz? Brady, you had a question.
Yeah, can you hear me?
Yes.
I am rather concerned about agriculture. As we heat up, I read an article not long ago, I've forgotten the species, but you know, the species in the ocean, if the temperature goes up 1 or 2 degrees, we're going to lose them. The agriculture in our country, things that have grown well in one section as the temperature heats up, they're not going to do well.
Yeah.
And you were talking about having to feed the world's people. It's going to get harder.
Especially if the population keeps growing on top of it all. And it still is, yes. Mm-hmm. The agriculture, I think the biggest problem I see is that it is already not sustainable. If you look here in the US and our, what do you call them, corn belt, wheat belt, all that, they are relying on irrigation a lot. In many of these areas, they are drawing down the water table. I think in Nebraska, it's somewhat sustainable, but there are other regions where they are drawing down the water table really fast, and they have to be really careful. Then there are water rights in California, for example, where they grow rice. I don't know if they changed this in the meantime, but along the West Coast, they have water rights that if a family used the water and keeps using the water, they have the right to do so from there on out. But if they stop using it, they lose the right to it. So of course they go and use the water, which causes a lot of waste in a place like California that's already dry. And this has something to do with the laws as well. If they lose it, someone else is going to use it. And we do have to be very, very careful with what we're doing. We should probably shift what we grow where. California should probably not grow things that require a lot of water. They should probably focus more on drought tolerant crops. And I'm not sure, I mean, you see the symptoms and the signs everywhere. And to tell you the truth, I think we need to figure out how to cut down on population growth. How to make sure that we don't need more and more. Agriculture always claims, oh, we will come up with a new invention, the Green Revolution, and so on and so forth. We will be able to produce more next time. But that just supplies more and to sustain the population growth. This is what it's done so far. And then the population outgrows the new production again. And we're fighting the symptom instead of the cause. Yes.
Yeah, I had a question. Thank you, Dr. Walz, for a very interesting and sobering talk. When you were talking about the flooding along the coastline, you made a rather bold statement about relocating rather than rebuilding, which I think I agree with in a general way. But my question for you is, how do we move in an orderly and systematic way toward having a policy for relocating rather than rebuilding?
Yeah, I do believe what we need first are new laws. We should not allow them to rebuild, basically. We are already investing money to help them rebuild. I think at the same time, we should just encourage that rebuilding elsewhere. I don't just think that this is going to be a migration away from our shoreline here in the US. I do believe that we are going to get a whole bunch of international migration from areas where, like Bangladesh, for example, they are pushing out. What would you have to do? First, admit that it's happening. The politicians, they have no interest in admitting it and doing anything about this. Of course, we are building a lot of structures that are not supposed to really survive 100 years. We may be able to do this a little bit longer. The Corps of Engineers, they are rebuilding structures on stilts. This may be a way to stay there for a little bit longer. At least you'll make it through storms that flood your area temporarily. They are building dams that may be breached occasionally, but I think areas like Florida, I don't know what kind of investment this would be to keep, you know, that a large part of the Netherlands is under the ocean, the sea level, right? They have built their dams and they are maintaining them really well. But of course, it's kind of a triangle that cuts into the rest of the continent. So it's just one side that needs to be protected. With Florida, you'd have to build this whole wall around it. And I don't know what kind of an undertaking that would be. In the Netherlands, they pump the water out. They have pumping stations to get rid of the water in the end. And I think California, there is a spot if the sea level was really to rise, worst case scenario, the Central Valley would be flooded. But there's just a very narrow spot where the water would enter because the surrounding of it would be too high. So that would be an excellent spot to build a dam. There it could be done. I see it feasible. Now, in terms of convincing people to move inland, politicians need to get involved, admit something is happening. But a lot of people are making a lot of money if something gets destroyed and you get to rebuild. And the sooner it gets destroyed, the faster you can make money again. I'm sorry.
After Superstorm Sandy went into New York, I have forgotten the amount of money, but the huge amount of money to try to protect New York City from this happening again. It's just so complicated.
Mm-hmm. Yeah, and there is obviously money there that's being invested, and I just think we need to focus that money further inland. Seattle is interesting. They built the new houses on top of the first story of the old houses. Maybe that's another way to build upward. They filled in the rest. So their first stories are now the basements.
Oh,
It's maybe another way to just build the new roads. You know, you collect so much garbage and roll and everything, just fill it in and raise everything one floor up. Sorry. If you ever get to Seattle, do the underground tour.
Well, thank you, Dr. Walz. This has been quite informative.
and
I'm
depressing.
Sorry about that. Sorry.
Well, it makes me want to go plant some more trees in our yard. We've had to remove trees because they were old and diseased and they would have
Yeah.
landed in our home.
Yeah.
And now I'm like, what can I put? We have put some back, but I need to add a few more for shade purposes. And you know, the oaks are nice, but they get huge and then they tower over your house. And if a storm comes along, your house is a little vulnerable.
Yeah, they would have
So-
to be planted further away for sure.
Yeah.
If you have a long lot, maybe.
We had a big oak that had to come down because honestly, it was half dead and it would have come through our home.
Yeah.
And I was really glad to see it go because it was a huge concern. But, and I do try to park in the shade always in the summertime. I do look for shade because I think it's better for my car. And I do wonder how we feed all the people. And my husband thinks I'm silly, but I'm like, I don't know how there's enough food. I think about that. I do think about that a lot.
Because
But
a
anyway,
lot of import, export, you know, getting food from elsewhere. And but if you watch the news very carefully, you can hear how the system is strained. How, you know, erosion, dropping quality. Did you hear the report this morning about the orange trees dying in Florida? The orange crop is going to be very low this year, and it's going to cost a lot to buy oranges this winter.
we actually order oranges from Florida, and we got in early because we got some before Christmas, and they're lovely. They are so good. So,
Yeah.
well, thank you. I hope your dog is okay.
Yeah,
And
checking in on him again. Yes.
Thank you so much for putting all this together and speaking with us. We've gained a lot of information, which is kind of our goal is to continue learning, to keep learning. Do we have any other comments before we let Dr. Walz go? All right, I don't think we have any, and thank you again.
Thank you for the opportunity here.
Oh, we were pleased to have you, Dr. Walz. Thank you again. All right, I'm going to let everyone go now. Goodbye.